Last time we talked about modular arithmetics, and we show that you can do addition, multiplication, and subtraction in modular arithmetic in the typical ways, but you cannot just divide, right? We cannot divide. But if our goal is to solve equations, okay, if our goal is to solve equations, like for example, suppose you want to find the value of x of these equations. So what multiplied with 5 modulo 7 gives you 2. If you want to solve these equations, we can solve it without having to divide, right? But naturally you can think of it as doing the divisions, but with natural numbers, there's no way you can actually do the division, but essentially you can think of it as division. So how can you solve this? Basically, in real number you would divide the whole thing by 5, right? But in modular arithmetic you cannot divide. You need to redo something else. So we want to get rid of 5. So we find some number that after multiplying with 5 give you 1, right? So if you multiply something with 5 and you get 1, this is like exactly like a way to get rid of 5, cancelling out 5. Okay? So, and we know that if you modulo 7, 3 is the guy that you're looking for, because 3 times 5 is 21, which is 1. Modulo 3 times 5 is 15, which is 1 modulo 7. So if you multiply the whole thing with 3, you get that 2 times 3 is 6, and then 3 times 5 is going to be 1. So you know that x is going to be 6. Okay? So if our goal is to solve equations, so basically division is a way to solve equations. Okay? You just ignore about, like when you are young, you say division is like you dividing stuff into equal parts, right? Forget about it, okay? We don't use that definition here. So division is a way to solve equations. That's that, okay? So what we would do is to use the multiplicative inverse, okay? This is the notation of the multiplicative inverse. You can think of it as 1 over 5, but it's not 1 over 5, okay? It works exactly like 1 over 5. And when you write it 5 to the minus 1, it's right exactly like 1 over 5. Things on 5, okay? But it's not, it's a notation that this is like the multiplicative inverse of 5, okay? So how can we, so if we have multiplicative inverse, we can solve equations. And today we will solve a lot of equations. So, okay, so the thing that you need to be able to solve equation is the multiplicative inverse. And we can find multiplicative inverse by brute force. You can just like try all possibilities and then you get what you want. But that would take you too long. Okay, now we will look at some particular summations, okay, to derive to find an inverse. There will be some. This is the expression that we will look at. Okay, so if we have two integers, and we prove some properties related to this. So if we take two integers x and y, okay, and then if we take another two integers a and b, and we write this expression. So we multiply x with a and we multiply b with y. Okay? These expressions, this term, we really related to GCD. Okay? Why is that? So let me show you something. Okay? So if I know that g dx, okay, and if I know that g also dy y, if we know this, what can we say about this term? Do we know that g also dy this term? Do you know that g also dy this term? If t divides x and t divides y. Yes, right? Because if t divides x, it means that there exists some number, right? Some integers k, integer, right? Such that x equals k times t. And also this one, if t divides y, we know that there exists integer l such that y equals l times g. Right? When you plug this in, when you plug this into this, you have a times x plus b times y. It's going to be equals to a times k times g plus b times l times g, right? And then this will be a times k plus b times l times g. And this is an integer, right? So since this is an integer, then we know that t divides this term. Okay? So if there's some number, some integer that divide x and y at the same time, it also divides this. Okay? What do we call g? What is g? When you look at x and y, what is g? G is a divisor, right? It's a common divisor. Okay? So if t is common divisor of x and y, it also divides this term. Okay? So any common divisor of x and y divide ax plus by. Okay? Does TCD of x and y divide this term? So let me conclude first. For all common divisor t of x and y, t is going to divide ax plus by. Okay. Can TCD of x and y divide this term? Yes, because a TCD is also a common divisor, right? It's the greatest common divisor. So since any common divisor divides this term, the largest one is also going to divide this term. Okay, so TCD. So in particular, so TCD of x and y also divide ax plus by. Okay. On the other hand, so if I know that there is some number that divide this term, if I know that there's some number that divide this term, can you relate that number with the TCD? Maybe, maybe not, because a and b may be 0. If a and b are 0, then you get 0, and then you cannot. It's really hard to relate 0 with anyone, right? But we actually know that TCD has to divide this number, okay? So if this number, if a and b, if this term ax plus by is really small, what can you say about TCD? TCD has to be small as well because it divides this number. So to divide this number, it has to be like maybe as large as this number. Cannot be larger than this number. Okay? So the thing is like, what if we find a and b such that ax plus by equals 1. So if you fix x and y, and you can find some number a and b such that ax plus by equals 1, what can you say about the TCD of x and y? So the TCD of x and y has to divide 1. Okay? So the only number that divides 1 is 1 itself, right? So if we can find some number a and b such that ax plus by equals 1, this would imply that TCD of x and y is going to be 1 as well. Okay, so this term is like is really connected to TCD. Okay, so if you can find some number a and b such that ax plus by is small, you can show that TCD is small. And if you can find that it's 1, then you know exactly that the TCD is 1. Okay. Also, on the other hand, if GCD is 1, okay, so this is one direction, okay? So you can find A and B such that x plus by is 1, you know that GCD is 1, okay? On the other hand, if you know that GCD is 1, we can find A and B such that they satisfy these equations, okay? So this is what we will try to do, okay? And this A and B is the same A and B as the one in your table. So let's conclude our discussion. So if this term is non-zero, okay, it has to be divisible by GCD because GCD divides x and y, right? So if it has to divide these numbers, okay? So if it's non-zero, then it has to be divisible by GCD. So the GCD has to be at least this number, okay? But you can actually find A and B such that this term is true. You can find fixed x and y. You can find A and B such that A times x plus B times y equals GCD x and y, okay? And with this, when we have this A and B, we can find inverse. We can find multiplicative inverse. Okay, so you can think of this as so the story is not simple. Okay, so let me give you the overview again so that you won't get confused. First of all, we want to find, so our goal is to find multiplicative inverse. Okay, so we want to find multiplicative inverse because we want to solve equations modulo something. Okay, so to find multiplicative inverse, we having to do something with GCD. Okay, we will find this A and B and GCD. Okay, to find the inverse. So that's our goal. Okay, so let's get more concrete. So to find A and B, okay, to find A and B, given x and y, to find A and B, we will use Euclid algorithms. Okay, we will basically modify Euclid algorithm to output not only the GCD, but it will also output A and B. Okay, so you output A and B so that in the end you have not only have GCD, you output A and B as well. Okay, to do that, let's see how we could do that. Okay, so we would modify the algorithm like this. Let's see. If you should recall this structure of GCD. Okay, so the Euclid algorithms, the original version contain this part, and then this part. Right? You just call GCD and you call Euclid y and x mod y. Okay. Now we need to return A and B. This is what we need to work on. Okay. Now let's look at the easy part, the base case. When x mod y equals 0, the GCD is y. Okay, the GCD is y. What we want to find is the following. So we want to find A. X and y is given to us, right? We want to find A and B such that A and B, ax plus by equals GCD of x and y, right? But in this case, the GCD is y. So in the base case, okay, so base case, this case, okay. So the GCD is y. So we want to find A and B such that ax plus by equals y. So what should A and B be? So y equals y, right? So we can set B to be 1 and A to be 0. So we can let A to be 0 and we let B to be 1. Then we have equations 0 times x plus 1 times y equals y. and that's the one possible value of A and B. So I would return A with 0, B with 1. Okay, so in the base case, Euclid algorithms return the GCD. If y mod dy x, I return y and 0 and 1. So this should be, you might think that it doesn't make any sense, but yeah, that's the value that works. Okay, so if when you do the GCD, if your last step is 1 and something, then A should be 0, B should be 1. If you have one additional step with 0, okay, you shouldn't have that step because the Euclid algorithm would stop when B is 1 already, right? Okay, so you can write down A and B to be 0 and 1. Okay, but you cannot just use 0 and 1 all the way, right? Because it only guarantees the value of x and y in this recursive call. So let me try to work on the sheet for you. So let's see. So let's pick some numbers. So let's try to do this real quick. So let me. Okay. So in this level, we know that the GCD is 1, right? So so let me explain this table again if you are confused, so that you know what we are working on. Okay. Okay. So it's like we call GCD 113 with 43, right? But 43 doesn't divide 113, so we recursively call GCD 43 27. So this is like 113 mod 3 43, okay? And we know that they are equal, right? And then it recursively called GCD 27, 16, and so on. In the end, it's called GCD of 5 and 1, and it returns GCD to be 1. Okay? But we also want to return A and B. Okay? We want A and B such that A times 5 plus B times 1 equals 1. Okay? So we want as a note, we want A times 5 plus B times 1 equals 1. So the value that we can choose is we would set A to be 0 and we set B to be 1 because it satisfies this equation pretty simply. Okay? Now, after the recursion returns, okay, this recursive call, this GCD, we call GCD 11 and 5, right? So it returns GCD 11 and 5 called GCD 5 1, and it returns 1 0 1. Okay, so this is G. Let me call G, it's G prime and A prime and B prime. This is the value returned from the recursive call. Okay, but we can return G to be 1 directly because we know that the GCD is the same. Okay, so this should be 1. However, we need to find a new A and B for this recursive call, right? For this recursive call, we want to find for this, okay, so let me write it here. We want to find A and B such that A times 11 plus B times 5 equals 1. Okay. In this case, we cannot just use 0 and 1 because you get 5 equals 1, which is not true. Okay. So we want to find A and B. How can we find A and B? So basically, we know A prime and B prime. We know A and B from the recursive call, right? We want to use this A and B to construct A and B for this recursive call. Okay. After that, we have A and B here, and then we can try to use the same formula to get A and B for the parent recursive call. So you think this, right? So you make one, you call GCD and GCD call GCD and call GCD. So these are like many levels of recursive call. คุณเรียกตัวเองซ้ำๆๆไปเรื่อยๆ Okay. In the last level, you return 101, and you need to use 101 to construct A and B for this level of the recursions. Okay. And we hope that if we know how to construct A and B in this level of the recursion, we can use the same formula or the same idea, same algorithms to produce A and B for this version and so on until the end, until the last version, the last level. We could figure out like some number, so we would return A, G up to this, right? And then we be able to find A in the top level. We would like to find A and B such that A times 113 plus B times 43 equals 1. Okay, this is the goal. Okay, but we do that recursively. So in the base case it's easy, but after that might not be that easy. Okay, so you know what we are trying to do now. Okay, if you have questions, you can ask now. Okay, so this is the code. So we want to find. So after we make a recursive call, we get A prime and B prime from this recursive call. Okay. So what property do we have from this A prime and B prime? So we know that from this. Okay. We know that when you make a call, this is X in the recursive call. This is Y in the recursive call. So you know that A primes times Y plus B prime times X mod Y equals G, equals GCD. Okay, so this is what we know. You know, A prime times Y, B prime times this equals to G. And we want to find A and B such that, so we want to find A and B such that AX plus BY equals G. So we have something really close, we have something times Y plus something times X mod Y equals G, right? But not in the right, not in the right form, not AX plus BY. But we can just work on it a little bit and then we figure out the actual coefficient that we need. So A and B are coefficients, right? Okay, so let's try to work on it. So we know that we have A prime and B prime from the recursive call such that this thing is true. So we know that Y has to multiply with A prime, that's one part. And then B prime multiply with X mod Y, but what exactly is X mod Y? So we write X mod Y in a nice way, in a nicer way, and then we'll see how it works. Okay? So what exactly is X mod Y? So X mod Y is what is left after you multiply Y with the division of X, right? So you have X and you want to divide by Y, right? So you have X and you divide by Y, right? But if you divide it exactly, then there's nothing left. But if you don't divide it exactly, then there's something left. Okay? So how many times can you divide X with Y? So it's gonna be the integer part of this. Okay? I'm gonna take the floor. You know these notations? So basically you leave out all the fractional part. You round it down. So if you divide X with Y and you get 1.25, so you take 1. Okay? So you round the number down. Okay, so this is how many times Y can divide X, right? So the remainder, what is the remainder? So the remainder is what is left after this, right? You see how it works? So this is like, you ask how many times can you divide X with Y, right? And then you multiply Y with Y. So that's the multiples of Y, the largest multiple of Y, which is still less than X. Okay, so this is X mod Y. So basically this is X mod Y. If you write it in another way, it's exactly this. Like if you want to compute X mod Y in Python, what do? So you say X minus X divide Y, right? So // is like integer division, right? So divide and then and then you multiply with y. So that would be x mod y, exactly this term. So now, if I know that this is x mod y, I can plug this term in to the equation, the top equations. This top equation you get from the recursive call. So you get from recursive call. Okay, so we plug x mod y in, so you get that a prime times y plus b prime times x mod y, but what is x mod y is this. Okay, so let's actually multiply everything out. So you get b prime times x, okay, and then what else do you get? You get a primes times y, then you get minus x over y times y. Okay, and I can factor out y. So this is equal to b primes times x plus a primes minus x over y times y. And I know that this equals to, this number, right, equals to t, right? So I know that this equals to t, equals to t. Okay. What do I get here? Now, b prime is an integer. Why do we know that b prime is an integer? Because it's the value returned from the recursive call, and the recursive call guarantee that b prime and a prime is going to be integers, so b prime is an integer. This one is also an integer because a prime is an integer, x over y. The floor, this is floor function. The floor of x and y is going to be an integer. So you subtract an integer with an integer, this is going to be an integer. So I know that these two integers, there is two integers, this b prime and this term, they are both integers, and the first guy multiplied with x plus the second guy multiplied with y equals to t. Okay, so this is what we are looking for. So this is our A, and this is our B. Okay, so basically you take the recursive call, give you this, and you do some calculations. Okay, extract all the numbers and then plug in x mod y, and then you rewrite a little bit, and you know that you have this term, you have this first part and the second part, and this will be our formula. You don't have to remember all this. Okay, in the exam you don't have to remember all this. You can, but I won't give you the formula. But you can take notes. Okay, you have three pieces of paper. Ajahn Thana gave you 4, right? Gave you 2, right? I wanna top up over that. I gave you 3. Okay, so I'm old. I give you more flexibility. So we have from that discussion, we know that A is B prime and B is A prime minus x over y with the floor. Okay, and that's the algorithms. That's the algorithms. So we'll try to work on that in your table. So let me try to actually do that. I'll show you this code later on again, okay? So let me work on his number to see how it works for a few steps. Okay? I'll show you this code soon. So let me But you should remember b prime, a prime minus x over y, right? So let me write the formula here. So a prime is going to be, a is going to be equal to b prime. B is going to be a prime minus x over y. Okay. So now, in this row, okay, a is going to be b prime. So a is going to be 1. When you look at this row, this is a, b, and this is a prime, this is b prime, okay? So a is going to be b prime, so this is going to be 1. So let's try to plug in to see if it works. So this is 1, and this is 0 minus x over y, and the floor of x over y. So 11 divided by 5, it's going to be 2, right? Because you round it down. So this is minus 2. Okay, so let's see if it works. So 1. So to check, it's going to be 1 times 11 plus minus 2 times 5. Is it 1? So 11 minus 10, so it's 1. Okay? Now, let's do it one more time. So now when you look at this row, this guy will be a prime, this will be b prime. So a, and this will be a, this will be b. So a prime, b prime will be my node. You don't have to write it down. Okay. So a is gonna be b prime. B prime is minus 2, and then b is gonna be a minus this 16 divided by 11. The floor of that. So you can how many times can you divide 16 with 11? 1. All right. Thank you. Okay. I made a mistake. Thank you. ขอบคุณครับท่าน TA. So okay. So I made a mistake. So b prime. So I made a mistake. Sorry. So my formula is incorrect. Oh, this is nice. Okay, my formula is incorrect. We will fix it. Okay. This is an example that when you work on math, you can always make a mistake, but don't do that in your exam. Okay. But when you make a mistake, you see it soon enough, right? When things doesn't work out. Okay. All right. So all right. So this is b prime. So b prime times x, and then there's a b prime here. I forget b prime. So that should be b primes times this. It's gonna be b primes times y. So this term is not just x over y. It's gonna be x over y times b prime. Okay? Now it should work. Definitely it should work. So let me fix this. I sort of like seem to be too simple, and yeah, I was wrong actually. Okay. So there should be b primes over there too. I'll show you the formula soon. So let me try to correct what I've done. Times b prime. So okay. So this is minus 2, and then this is gonna be a, so it's gonna be 1 minus x over y is gonna be 1. The floor of x over y is gonna be 1 minus b prime, but b prime is minus 2, right? So it's gonna be minus 1 times minus 2. So it's gonna be 3. Okay, it's gonna be 3. So let's see if it works. So let's plug it in. So minus 2 times 16 plus 3 times 11. So minus 2 times 16 is minus 32.
3 times 11 is 13, so it's going to be 1. Okay, so this is A and this is B at this level. And you can keep plugging in, okay? So this is going to be 3, this is going to be minus 2 times plus something times something, okay? So that's how you would work on it, okay? So after that, if you try to fill out and you reach this point, you should get two numbers A and B, and you can try plugging in to see if it works. Okay? Just plug in the formula to see if it works. Alright, so let me show you the algorithm again.